Good morning, everyone. So thank you for showing up. I hope we don't make you all sleep. I really hope so. Sorry, just a minute. I need to start our timer here so we don't lose yourselves on our thinking. So before we even start, I want to make a disclaimer, okay? So we work for Intel, but we do hardware security validation, okay? We don't work for the Intel Security Group. We are not related to what the Intel Security Group develops or researches. So that's just a disclaimer, just to make it clear. And all bad jokes that we make and all mistakes that we make, that probably there will be many, are ours and only ours, okay? There is no other people to be responsible for that, only ourselves. So, as a part of the disclaimer, I also want to say that never trust someone who shows up and starts showing you a lot of data, okay? Because the data always lies. So we'll try to lie a little bit less, but that will be a lie as well, okay? So we really will throw you a lot of data, okay? I ask you to pay a lot of attention on the methodology on how we collected that data, because it makes a lot of difference. Okay, we try to be very specific and make very specific comments on how this data was collected. So a big part of this presentation is basically explaining how we did that collection. And the way that you collect the data, it will really affect the visualization of it. Also, sometimes we will compare things that are not really a good way to compare. So we compare, for example, two different data sets. So when we make that mistake, we will tell you, okay, that we're comparing data that supposedly were not comparable, okay, just to let you know. Also important to say, we are from Brazil, okay? Brazil is a very fun country, okay? We have the carnival that everybody knows about. We had the World Cup. Brazilians respect everyone but the Germans, of course. But after this research, we really respect the sysadmins. Okay, so this is a picture of our machines, the ones that we use it for processing the data that we're gonna show. And sysadmins are essential to keep the system running. The machines fail, the hard drives fail, the operating systems don't behave as they were supposed to. And as more data as you have, as more subtle bugs will show up, and we ended up having lots of them. So we do really respect a lot the sysadmins after that. But to be honest, this is more a real picture of our machines and our installation, okay? So this is the living room of my place. So the machines were all around because the house didn't support the energy that we were using. So everything starts falling down, and we needed basically to move machines everywhere. So it was weeks without watching television. So, just for the agenda, so I will introduce a little bit about the motivation of this research and what we're trying to do, show the objectives and some of the good things that we believe we can actually find with this kind of research, and then explain the methodology. And after that, it's basically showing you the data itself that we collected. There's lots of materials that we generated, lots of information is basically raw data, things that we didn't even parse. But if you have specific questions to this kind of data that we collected and we don't show it here, send us an email and we're glad to help you either trying to process our data or just sending you the raw data itself so you can process yourself. Okay, so the idea here is really to just share, okay, share information, and there will be some things that you can actually learn with this kind of data, and we hope more people will start sharing it. So the motivation for this talk is very similar to the one that we gave 2 years ago. And to us, it's kind of a surprise that the motivation remains the same. So basically, we know there's hundreds of new samples every day, hundreds of thousands of new samples every day. Okay, so we see the companies saying that. We see the numbers, but it's difficult to understand where those numbers are coming from. And when the same companies, when they actually release data, for example, detection data that they release, or some other statistics that they release for specific mechanisms, they only show a couple of millions. So we thought, okay, if there is hundreds of thousands new samples every day, a couple millions is not enough to actually be even relevant. So we decided that we needed to collect more than just a couple of millions. That was the challenge that we had. So the idea was like, okay, we're just going to look into what the malwares are doing, and we will start like seeing, okay, instead of like just a couple of millions, let's try 12 millions, and let's see what is that. Let's see if the data shows us something interesting. Lots of those data is just not interesting at all. And some of the questions that we had, we're gonna show, we didn't manage to answer, okay? So that actually demonstrates how complex malware is and how much like we need to share in order to actually learn more. Also, it's important to mention that when the industry is sponsoring, like guys, like the industry has like the best minds, okay? Like the best guys in reverse engineering that I know work for AV companies. The matter is like when they do research for the companies, they need to give the results that the company is expecting, which means people only look for things that are interesting, things that will actually manage to show up at Black Hat, right? So, and that's a problem. Sometimes some things that are very simple, nobody actually look into that. And maybe there is interesting things to learn even in the very, very simple points. So we try to actually collect those here and demonstrate it. And before we even continue, I really need to say thank you to our sponsors, right? Our sponsors actually let us do the research without actually like being affiliated to anything, without committing to any results. And I really, really wish our sponsors were also sponsoring Black Hat, but they are like very small in budget, so they couldn't sponsor Black Hat, so they asked us to say shoots to hand. So those are our sponsors, okay? So basically, don't expect us to show results that are based on the industry, okay? We just like went like to Gizmo's hardware and we bought the machines ourselves and we just started like analyzing data, okay? So we don't have commitments with that data, we just show it. So just like some introduction on the terms that we're going to be using. So for the 2012 research, we basically look into like protection mechanisms that the malware employ. So we're gonna continue and extend that to all the data sets that we have now. So we're gonna talk about anti-debugging techniques that the malware employ, anti-disassembly technique, obfuscation, and anti-VM. So we're gonna discuss those points and also show like some new things that we brought on that field. And also we introduced like a new one that is, we will call in this research malicious technique. But really we're using poetic license here to just define something as we want, okay? So when we say malicious technique, that doesn't mean because a sample uses a specific function, it's malicious just because the function is there. It's just like we had no better name to say. It's something that we looked at after in all the samples that we collected, and we're gonna show you the precedence. Because something is there doesn't mean it's malicious. Okay? Don't think that this research tries to define maliciousness, because that's a problem that is not really solvable. Okay? What we're trying to do is just like collecting what is common between all the samples that we saw and show you the numbers. Some of them, only look into the numbers, you will say, hey, I can just block samples that have this specific characteristic because nothing benign will have that. Some others, you just need to use like as one of the points for you like to do a block decision. So what we did for this research is basically, we analyzed like millions of malware samples, and we're gonna share like the results. So for the techniques, for the protection techniques the malware employ, we basically updated the results from the previous talk. We also removed some of the limitations on the way that we collected the data, and we also changed the methodology for the data set. We're gonna compare the data, but I will explain that they are like kind of different when we compare them. And also like there is like the other techniques or other characteristics that we just decided it was interesting to have a look. Some of them in the end are not interesting, but some of them actually are. One thing that is important also to say is we proposed lots of improvements on the way that you collect that data. Some of those improvements came from feedbacks from researchers actually. For this data set, we decided to not filter it. But we're gonna show you how you could filter better, okay? We decided to not because in the end we end up like with like a billion basic blocks for like differentiating malware. So like a billion was like too big for us to process. So we decided to not use that in our data selection. But I will explain a little bit more later. So we also made like a project decision. For the previous talk, we developed like a big framework. We had plugins. We had like something that was like very easy for someone to contribute code and like to get results from the platform. But in the end, we never received like a really good contributions from the researchers. So what we decided is like, okay, instead of like supporting something, expecting contributions, let's just redo everything from scratch, but being much simpler. Let's put all together like more performance for us, so we actually can like process more samples. So basically, like, just like for you guys to have an idea, I will show like the number of cores that we had in the processing and the number of memory. But basically, for processing the 12 million samples, it take us around like 10 days. And for parsing the results, it's like 72 hours. So all the results you're gonna see here, basically like we can recollect everything in 10 days with 4 machines and 72 hours just to parse it and show you. So like if there is any data that basically we didn't get and you have interest, we can write the parser and probably in around 72 hours we can provide you the result. Good. Also important, because of this project design decision, so which was more like we started doing it and then it became our architecture, right? Just because of this decision, some limitations showed up. And we only figure out those limitations when we started creating the graphs. So for example, in the past year, we managed to, 2 years ago, we managed to show you samples that had like common characteristics. So for example, from the package samples, how many of them have this specific protection mechanism employed? Nowadays, the way that we wrote the parsers, they basically collect the global numbers. So we lose the state. So we don't have a way, like with our parsers, to actually provide that collection. So we're gonna explain that when we show some of the graphs. Of course, that limitation is just a matter of like rewrite the parsers and 72 hours. Okay, so it's a limitation in the data that we show, but it's not a limitation on the whole data that we collected, which is more important. So basically what we have now is like 80 cores, so it's like 10 dedicated machines, 2 of them are blades. That's one of the problems that we had. So like we had 2 blades that were like supposed to be 8 machines, but each blade only supported to really run full, using all the power, all the processing power, only 3 machines instead of 4. So we needed to run up and go and buy more machines to put. So that's how we end up like breaking everything around the house, like to put more machines. We only analyzed 32 bits PE files. So I don't think like if you consider 64 bits or even like ELF malwares that the numbers will change too much. But I don't know, we didn't look into that. So maybe the numbers will change. Also in the previous research, we decided that each sample that was packed, that we saw, we only counted as a 1, because the packer changed the characteristics of the sample. So we thought that, okay, the packer will change the statistics, because if a packer is prevalent, it's like in 90% of the samples, the packer alone will change the statistics of everything. The matter is like nowadays, the prevalence is more like server-based mutation, not necessarily package samples. So we decided to remove that limitation. So when you see a number here, the number is really compared to the 12 millions. So the number is really like what we've seen. So if we say like, okay, this characteristic shows up in 10% of our sample set, that really means 10% of the entire sample set. Okay, we didn't eliminate packers this time. Also, like we appreciate like the feedbacks that the McAfee researchers gave to us about like the previous data set. So we shared the shell ones of the samples that we used, and they found that 23,000 out of our 4 million samples were actually not malicious. So that's cool. Like the sample set that we use now, this time is public sample set. Prior to that, it was like basically coming from companies. This time it's totally public. So that means we went like to ViralShare, like VX Heavens and those kind of projects. We talked to the guys and they sent us samples and we used those samples. Okay. So for the previous research, the McAfee guys found out there was 23,000 good binaries there. Okay, 23,000 actually didn't change the statistics. It was irrelevant for the statistics because it was like 4 million samples. We don't know how many of those samples now, out of the 12 million, are maybe good. Okay, we don't know. We're trusting the source of the project that is providing us samples. And again, saying if it's something is malicious or not is just not possible. Okay, so we can have good indicators, and we hope the numbers, the prevalence numbers actually will demonstrate that our data set makes sense. but we don't really have an easy way to know, okay? So keep that in mind when you look into the data. Also, in the previous year, we had a limitation on the size of the samples. So the limitation was more due to the way that the machines were connected to each other than anything else. So we had like a size limitation that the samples bigger than 4 megs we were completely ignoring. But nowadays, since like lots of the malwares are like coded in higher level languages, we suppose that this limitation is not really good, so we removed it. So we analyzed samples like any size. And actually it's cool because some of the bugs that we found was because big samples generating like really a lot of data that we were not expecting to parse. So also like in 2012, we did the data set cleaning basically using like the packer information that we managed to collect. So it was basically Yara rules, like for defining packers, which means not necessarily is like perfect science, right? And also we used entropy information. So like higher entropy samples were like ignored because we considered them to be packed, but we didn't detect the packer. For this year, as I mentioned, we decided to not go for that. Anyway, like one thing that the McAfee researchers brought to us, and it was like interesting, is like samples like Salit, they generate lots of variations that have different hashes, but are in the essence the same sample. So we wanted to have a way to clean that data set from this kind of cases. So we actually developed the code for doing it. We have it, the algorithm, we will publish even the algorithm. But the matter is like, in the end we had like 1 billion gadgets, right? So 1 billion basic blocks that we could use to compare to each other. And then it was like an explosion of comparisons. And we just thought it was not worth it. So we didn't do that cleaning, okay? Just to make it clear. It's possible too, okay? It would just take more time. Okay, probably we go like what we're doing now is like lots of the things that we decided to not cover. We just like keep the machines running. We will collect that information and publish later. Okay, so I will put the links later also where you can find that. Yeah, and as I mentioned, like what the McAfee researchers they found out was like 23,000 of our past samples were known good. So if any other guy wants to go and see against their own base of samples and tell us what is a red good sample or what is definedly malicious, so you help us to be sure that the statistics are good, just drop us an email and we will like be glad to provide you the MD5 list of the samples. So this year we went for the MD5, not shell ones. Speed. So our methodology also only involved the static analysis. We kept that. So everything that you see here, we collect only with static analysis. We try to be as simple and as dumb as possible, okay? Trying to avoid like any kind of complications on the platform. The idea for static analysis is just because it's clear the benefits, it's very fast. And the malware can't do much against us, right? We running, the malware is not. Of course, there is drawbacks. There are like lots of limitations on the static analysis. So keep in mind those limitations when we're discussing the numbers. Most of the times what we tried is like any limitation that we face will only make the numbers higher, not lower. So we try to make that like really what happens all the time in the system. Which means that maybe we don't detect a technique that is there, so the number will go high. But if we detect, if we say the technique is there, it's because it is. Okay? So keep that in mind. The statistics are only going up, never going down. Actually, that's our intention. Maybe we made mistakes. We expect not. So, of course, also like we expected the prevalence numbers to actually go even up. If you use dynamic analysis. We just know it's not just feasible to analyze everything. That's discussions that we have with like all the guys that we know like in the industry, and we talk about, hey, what are you guys doing? Like these companies, they have labs that are huge, right? Hundreds of machines. But they also have their limitations, right? They need to collect information that they will use for actually generating the signatures. So they also have limitations on what they're collecting. So that's why we decided to go for static analysis and say, hey, maybe there is interesting things there. We didn't cover at all dynamic analysis in this specific research. In the previous one, we even covered some parts of dynamic analysis. On this one, we just don't, okay? We don't even have VMs running on the machines. In the previous work, like what we did like for collecting the protection mechanism was basically go and read all the blogs and papers, like conference released papers, things like that, and collect the techniques that people were talking about malware were using. We documented those techniques and trying to actually see the prevalence. We find out that it's really sparse, the documentation. So it's really difficult to actually do this kind of research because it's not only writing the code or getting the samples or getting the machines, it's also finding what you need to look for. Because like people are talking like very sparse. So a researcher finds a malware is doing something interesting, he publishes a blog post on that, which is super cool, he's adding information to the industry, but nobody's actually putting that information together. So you can have like that in one place. So we did that like 2 years ago. And for this year, like the techniques that we found out, were basically like in this past 2 years, we were looking to samples and seeing and making notes of interesting points. And also we look into like comments that other researchers made about specific samples, and we just made notes. And at the point in time, we sit together and we're like, okay, we have enough notes for a talk now. So let's detect those characteristics and just talk about them. So that's what we're demonstrating here. So there is no really science on the way that we decided to get those techniques, okay? It was more like we started collecting around. None of them is like our ideas. It's just like, okay, someone saw that there is this crazy sample with a crazy section name. So we're like, okay, maybe crazy section names in a sample is something interesting to look after. So we decided to collect that. Also, like, we try to not be biased in favor of like some specific samples, but it's difficult to say we are not, right? Maybe one specific characteristic that we detect is prevalent in a sample that shows up like in the huge majority of data, so maybe there is some biased data there. It's difficult to say there is not, but hopefully we did a good job on avoiding it. Every time that we detected something, so basically like we have 3 results for our detection scripts basically. So one is we detected, the technique is there. The other one is there is an evidence of the detection. So probably the technique is there, we are not totally sure. And the other one is the technique is not there, okay? So for the numbers we tried always to put together like it's not detected with the evidence is there, to actually do what I just mentioned before, which is like the numbers go higher, not down. There will be exceptions though, exceptions just because some things we needed to make an exception. Like for example, the sample is importing a function. Maybe we didn't find the sample is calling that function, but wow, it's clearly importing it. So we assume that the sample is importing, that means it's calling it. So that's a big assumption, but we make it clear on the data that we're making that assumption on this case. So also, one limitation is like, for the analysis, we always rely either in the entry point or in the executable sections. So if there is sections that are referenced, for example, by the entry point, but it's not executable, we did not analyze those sections. There will be exceptions, but we will mention them more like when we try to detect what the sample does once it knows it's being analyzed. So we needed to make that exception in that case. But we will make the case clear. Also, like we try to remove all the dependencies in any platform. So basically imagine that our analysis is a bunch of scripts running. Some of them are Python, some of them are C code. That's it, okay? That's our analysis. So that said, it's time for like Gabriel to come here and explain to us the results. Thank you again.
Hello. Okay. So for this research, we added 8 million more new samples. In which those we found that 22%. I don't know if it's possible to see in the chart because of the blue color, but the number is 22. More or less 22% were not PE32-bit files. So for the rest of the research, the numbers, we are going to consider only the PE32, as mentioned by Rodrigo before. Okay. So on the left side, we have the 2012 results, and in the right side, we have this year results with much more samples. These charts show the prevalence of packers in the malware. So we see that the numbers are really close to each other, right? So it's kind of consistent with other research. So it means that we got a good sample set, or or these two sample sets are equivalent. So it's a good number. And yeah, the number here is 37% more or less of the samples that we analyzed are actually packed. Okay, here is the top 10, actually top 10 packers. On the left side, the 2012 results. So as you see here, UPX was the most used, including all the variations of UPX, okay? And if we see the charts of this year, it's more or less the same. You can see many UPX because we did not group it in only one as we did in the last year, but they are more or less equivalent. Yeah, what happened is that the PE compact was one of the top, and in this sample set it's not actually one of the top, but as you can see, all the numbers are more or less the same, okay? Well, last year for the research we made a paper, as Rodrigo mentioned, collecting all the techniques we studied, we analyzed, we researched. And this year we also have a new one with the new techniques using here, but it's pending legal approval to be published. Actually, it's pending us to write and then send to legal approval. So, anyway. Okay, now I'm going to start talking to you about the anti-reverse engineering techniques present in malware. All of these charts that has some kind of correlation with the 2012 presentation will be together here. The idea is to compare, to see how the new sample set changes or not changed something in the other one. Here, it's important to mention something. On the left side, every time we mention the 2012, I'm going to talk all the slides of that, make it very clear. The percentage is not related on the total number of malwares analyzed. So for instance, you see the technique in 94.something%. It means 94.something% against the samples with some anti-virtual machine technique, okay? And on the right side is the comparison among the whole sample set, okay? So the nature of the data is not the same, but we can compare. I have here the numbers of the 2012 for us to see more or less.
So also it's important to mention that when we say 2012 and 2014, we are not claiming that the samples are from 2014 or the samples are from 2012. Yeah. We're just saying the results from our research in 2012 and the results from our research in 2014. I don't believe that numbers are saying, hey, this is the amount of samples in 2014. It makes no sense. You don't know if the sample really started to be released in 2014 or you only started detecting it as malicious in 2014. So that number is not trying to claim the samples are from the year. It's just like from our research on that year, okay?
Yeah, and it's actually not really possible to have this information, right? Yeah. You say, okay, this malware sample was developed this year. No, we don't have a global data set of malware samples, so, okay. So 2012, we got 81.4% of all the samples have at least one anti-virtual machine techniques, okay, at least one. So this year, so it means that 93% on this amount, it's equivalent to the one we got this year, that is 79%. So we can see that almost all the samples have at least this technique present, the samples we analyzed. The same for the other techniques. All of the techniques kept the correlation. Okay, then the percentages are different because of the nature. One is relating to the samples with anti-debugging, and the other one with samples with on the whole samples, whole sample set. Okay. So the in is still the most prevalent in most of the samples. Okay, anti-disassembly techniques as well. So we still got the fake jump. And the number of anti-disassembly in the other research was 12%. So if you see here, it's more or less the same, right? 71% of 12%, here it is 14, a little bit more, but actually it kept the correlation. Okay, so for the anti-disassembly, we see that 14% still have the STC-CLC technique. Okay, all the techniques are actually documented in our paper, okay? All of them. Even in the paper, the presentation of the past year, we mentioned in the presentation itself, the section number on the paper that's gonna be the technique. In the presentation as well is here. You see later all the techniques and in which section of the paper it's described. Okay, anti-debugging techniques. Here we saw an important change from the 2012 research. As you can see, the most prevalent technique in 2012 was the PB being debugged. Actually, this is not the is debugger present, it's actually the malware accessing directly the bits that this function implements. And it was the more prevalent in the 2012 data set, but in this year, it's not, as you can see, it's 0.64%. It's actually not really prevalent. We think this is because some packer that were not detected as packer were in the middle. And as we saw, 37% of the malwares were packed. So in all the rest, probably there is a packer or something a malware using that is changing this behavior. Okay, because this is the only, I think, important data that changed. So for this year, the technique that we most found was the anti-hook. Actually, the malware trying to detect if it's hooked. Detours. And okay, these were the most important. All the rest kept more or less the same. Okay. For instance, the SS register and the software breakpoint, they switched place, but the number is kept more or less close. Regarding obfuscation techniques, as you can see, the push ret is still the most prevalent. So in 69% of all the samples analyzed this year, we got the push ret obfuscation technique. It's also something close to what we had last year, except with the push pop math that have a little bit less in this new data set. Okay. Okay, we got some functions of interest, as Rodrigo mentioned. These functions, if this function is used by a sample or by a binary, it does not mean that this binary is malicious. This is not what we're trying to do here. But these are functions that is interesting. For instance, create file, get proc address, get open process, and all these kinds of all these different functions. And as we saw in this chart, 70% of the malwares we analyzed have get proc address using somehow. So you can infer here that the libraries are not being called directly. They are actually trying to get the address. This could confuse the analysis, right? Because you don't need something in import or something. And interesting data here to mention is the write file. As you can see, 45% of the whole data set when analyzed has at least one mention to write file. This mention is in both the EAT, getting in the data like load libraries or something, all the different ways we could get statically to get data is there. We see that 45% writes a file. So the approach of actually running a malware in a virtual machine and see the changes in the file system, it's actually kind of relevant here because that almost half of the malwares do something regarding. It does not mean that, as we mentioned, the number will always grow, never go less. Yeah, I think this is the more, and the other interesting here is the is debugger present. You can see 14% of all the data set has the is debugger present function being used. Number of sections, what we did, we got the whole data set and extracted how many sections the PE file have. So we ranked it from the 0 to 30. So 0 sections, 1 section, 2 sections, and then more than 30. And we got here the top 10. So we can see here that 32% of the samples has 3 sections, okay? 20% more or less have 5 sections. We can see that there are 3 most prevalent. So in the whole data set we analyzed, 4, 5, and 3 are the 3 big numbers of sections we found in malware. This is an interesting number. And now, what we did, we got the malwares, we got the sections, but we analyzed only how many of these sections are executable. The same story. 0 sections means 0 sections executable, 1 section means 1 section executable until 30 and 30 plus. And we see here that 61% of the whole data set of all the malwares we analyzed have only 1 executable section. Only 1. And then followed by 28% more or less that have 2 executable sections. So these are, if you put these 2 numbers together, so most of the malwares we analyzed have 1 or 2 sections that are executable. This is an interesting number as well. And then what we did, we did another try, and then we got section names. We got the sample set, extracted all the section names we found there, and we put it together, all these names. And we put here some top N. I don't know the number here, probably 12 or 13, but we got the most relevant one. As you can see, 81% of all the malwares we analyzed have 1 section called RSRC. This is the most prevalent numbers. And then followed by .text, .data, .rdata, reloc, and on. Interesting here to see the UPX section, the sections on UPX. Actually, this part of getting section names is really fun, because when you got all the section names, there are really fun names, like bad words, or someone cursing you, or some jokes. We see all these kind of things, but they are not among the top 10. And we also see many sections that does not have ASCII characters. So it was even a problem to us, because the /n, the new line, was actually one of the characters of some sections. And our analysis in the beginning was just relying on lines. So it was misaligning everything. So we were fooled, but it's interesting. We are showing that we were fooled. And okay, these are the numbers. And interesting here, UPX, that appear a lot, okay? Okay, now what we did. Okay, we got all the names. Now, how many, let's put it this way. Have a malware with a section text. If we got a section, for instance here, the data section, we got here this percentage that have 2 sections called .data in the same binary. We got the repeated names in the same sample. So this is the number about. So the same section number, section name, appear more than once in some samples, and these are the numbers we got. We saw here that the blank section, a section with nothing, in 1.83% of the malwares appeared twice. So this is kind of weird, right? If you get a malware, you see, hey, a section is blank. Oh, 2 sections is blank, so it's something strange there, at least, okay? That's why it's here, and then, okay, that's fine. These numbers are low, but they are interesting. Empty EAT. We also saw how many of the samples have an empty EAT, the import table, right? And we saw that only 3.67% of all the samples analyzed have an empty EAT. This is another example, right? A number that is small, but actually it's interesting because we did that. And now we know that almost no samples have an empty EAT, right? So if you do a parser or scripts like us, in the hurry, our applications is going to crash 3% of the case, right? So this is at least one. Okay, entry point attributes. Here we got the section of the entry point. We saw if it's writable, executable, read-writable, or not read and not writable. You got, right? The 4 combinations here. And we saw that 61.82% has the entry point section is executable and not writable. This is the most prevalent case here. Followed by both executable and writable. You see that, so that almost all the malware we analyzed has the entry point section as executable, because there are some samples that do not put executable, try to trick some analysis tool or something, but most of the malwares don't do that, okay? Okay, now we did more things. We got the first 100 instructions of all the malware. And we rank it. The idea here is to see, the the most prevalent instructions that appear in the first 100. So you saw here that, oops. No, yeah, I was talking in the next slide. I was looking on the right here. Sorry about that. We listed the common instructions to be present in the entry point, to be the first instructions we listed. And we saw that for 17% of the malwares, we found no uncommon functions. So all the functions there are common. Interesting to see that almost all the rest has at least one of the uncommon functions to be there. Oops, sorry, instructions, okay? Yeah. Okay, now the chart I was talking before. We saw that the add instruction appeared in 93% of all the malwares in the first 100 instructions. And here we ranked all of the instructions that present with the prevalence. So add followed by mov, push, XOR, compare, sub. Yeah. And here we saw that in Intel ISA there is more or less 1,300 instructions. Looking to the malware sample, almost a half, 625, different instructions appear. So half of the whole ISA appear in the first 100 instructions of the malwares. We saw that 5% of the malwares does a sleep just in the first 100 instructions. So the malware execute in the first 100 instructions, then a sleep. This technique used to fool the dynamic analysis. So the malware keeps waiting, and then the system gets a timeout, and then stops processing the malware. So this is there. We analyzed some P header, okay? Some characteristics or malfunctions or I don't know, something strange in the P header itself. Bad constructions of the P header itself. And we saw that 53% of the malware has a zero header checksum. It's zero there. And 27 has an entry point that is not in the first section. And then 22% there is overlap on sections. So a section that the initial and the size does not match with the alignment. We saw also that 22.7% of all the malwares are signed. All the rest are unsigned. The compilers, we see here, most all of the compilers that we detected that is not unknown is actually from Microsoft, Visual C, Visual C++, in different flavors. That's the most interesting data to get here. Section entropy, we saw here by this chart that 114% of all the samples have at least one section with between 0 and 1 entropy, a low entropy, right? Why this number is more than 100? Because we saw each section. So if a sample has 2 sections with this range, it's counted twice here. It's how many sections on that entropy range. And interesting also to see that high entropy is 74%. So if you get a malware of our data set, 74% of all these malwares have high entropy. Okay, that means probably packet or something different. We saw also vulnerability prevention implemented by malwares. We see that the safe execution handler is present in 79% of the malwares, ASLR in 15%, and so on. So the most prevalent here are the safe execution handler is used by malwares a lot. Okay, now Rodrigo.
So the matter is like with all those numbers together, you start seeing that the malwares they have lots of things that are clearly malicious, right? If you put it all together, probably you can block a lot. I'm not saying you can, I'm not saying it's easy, right? I'm just saying that we look into all those data. And when you actually think about that together, it makes no sense that a sample, for example, don't have like the checksum matching, or like the sections are not aligned, right? There are things that just makes no sense. When you look, for example, into compiler's prevalence, why that's relevant? Just because when you're writing like your detection scripts or when you're writing like protection code, you need to consider like optimizations specific for compilers, right? Since we know that the huge majority of samples will use Microsoft tools, do you really need to care about all compilers, or you care only about that ones, okay, or the ones very specific? So sometimes we make excuse because the problem is challenging. But those excuses, when you look into the data set, I can't understand how come we still see samples that have, like, for example, no names on the sections, like sections that don't align. That makes no sense. Those samples were supposed to be blocked, okay? I don't understand why they are not. Maybe there are like other challenges that we are not figuring out, and that's one of the future that we propose for you guys to do, or future research for us, which is like get a huge collection of normal binaries, like good binaries, and let's see if the good binaries also have those characteristics or not. I don't know. I am confident that they don't. So just because like we need to actually finish, we actually explained each of the techniques, each of the characteristics we detected. We have a section in the paper that explains it. Okay, so if you have a question of, hey, how do you guys detect that specific one, refer to the paper. Okay, as a bonus, we say that we try to look into, okay, what the sample does once it knows it's being analyzed. We failed to actually give you the result that we wanted. Okay, we wanted to come here and say all the samples we refuse to run, or we will skip, or will not do a malicious behavior, and then our recommendation was going to be, hey, just mimic as you are analyzing all binaries in your system and you are good to go. But the matter is like, it's difficult. Okay, so the way that we did is basically like we look into like, okay, the technique was detected, we look into the 100 next instructions. If there is any flow change, we follow the flow, and also we follow like the not taken of the flow. So another 100 instructions on each side. And then we try to see if the sample is calling exit or sleep, or what the sample is doing once it knows. Also, we look at if the sample is doing it and is using load library, which means maybe we missed something that the sample did for importing. So we try to show that, but in the end, the result's not super interesting. We found like more than 100,000 of samples just using that very simple way to detect it, but we still need to come back with better. Okay, we will improve that. I still believe the samples will not do anything malicious.
Yeah, it's not proven that it's anything malicious, right?
Yeah, we don't know, okay? The data don't support our claim. We still think so. So as a conclusion, thank you guys. Like there is lots to do. I really hope someone helps us with like the good binaries as well, and trying to show the same kind of data like for normal binaries, just so we can see if it makes no sense to let a binary behave like this. And all the stuff will be on the website. And this is our emails, like if you have questions. Thank you very much.